Hi everyone, and welcome back. I hope everyone had a not too stressful time working out that probability distribution. Okay, so here's where we left off. We were working on the sampling distribution for a small population, and the first step we figured out what each possible sample could be. So our first draw would be this, our second draw would be this. What would that look like? Every possible sample for a sample size of 2. And then from there, we all worked out, hopefully, the means of each possible sample. So here's what that first step should look like, or that first 2 steps really should look like. Here are all the possible samples we could draw. We could first draw a 2, and then a 2, we could get a 2, and then a 4, etc. And then on the right, you see every possible mean of that sample. These means are essentially now our new population for thinking about a sampling distribution. This is our data set. This is the data set that we now want to describe. This is the population that we now want to describe. It's the mean of all possible samples. So let's start the next step, figuring out the mean and standard deviation of this new population. So hopefully you guys found the same thing here, a mean of 5 and a standard deviation of 1.58. Remember, you're looking at a population standard deviation here. And from there, we can also draw up a frequency table. Here we see how often each mean came up in the distribution. Remember, frequency tables from a couple of weeks ago are about how often a score occurs, not about each individual score. So how often did each mean come up? And then, of course, from there, we can use our frequency table to draw out a histogram and see the shape of the distribution, which, as we can see here, is just about perfectly normally distributed. Let's take a quick second and go back to our original population. Take a moment here and calculate up your means and standard deviations for the population and see if you can draw just a quick histogram for it. So if you did that, hopefully you found that we got a mean of 5 and a standard deviation of 2.24 and essentially a flat histogram, right? There's only one of each possible score. And so this is what the actual population looks like. So if we go back and compare this to our sampling distribution, what do we see? Well, just like there are 3 main ways to describe any distribution, there are 3 main ways to compare distributions. So first, we see that the sample distribution mean is the exact same as the population mean. They're both 5. The sampling distribution standard deviation is different than the population standard deviation, though, 1.58 versus 2.24. And the sampling distribution shape is normal, but the population distribution shape is not normal. The population distribution is flat, but our sampling distribution turned out normal anyway. Now, what's really neat about this information about our sampling distribution is that we know that if we have a normal distribution and we know the mean and standard deviation of that distribution, we can pinpoint the probability of being at any point on this curve. That's the advantage of having a normal distribution, right? So that means for any sample we take, any sample we have a mean for, we can say how likely it is to have drawn that sample from all possible samples. That is, if we got a sample and we knew that the chances that the sample we draw from this population, the mean would probably be would have a 68% chance of being between 3.42 and 6.58. And we know that because we know the shape is normal and the mean is 5 and the standard deviation of this distribution is 1.58. And then by the same token, we know that if we pulled a mean of an 8 or a 2, that would be quite unlikely. I pulled a sample with a mean of an 8 or a 2, that would be quite unlikely. So we can start assigning probabilities to getting any particular mean of a sample, getting any particular sample with a particular mean. What we're doing here is we're converting the descriptive information about our sample into probability information based on what we know from the sampling distribution. And that works great when we have the entire sample. We know the entire population, and we can draw a sampling distribution based on every possible sample of any size from that population. But most of the time, we don't have an entire population of scores, so we can't draw out every possible sample. We're only going to have the one mean of the one sample that we're able to draw for our study. But we still want to be able to say the same thing. We still want to be able to say the chances that we would get that sample from that population, or that sample from that sampling distribution. And so we still want to be able to convert the descriptive information we have into probability information. And the good news is, through the magic of mathematics, what we found for our particular sampling distribution is actually the way almost all sampling distributions turn out. And that's governed by what's called the central limit theorem, which is a mathematical theorem that basically just for any population with a mean of mu and a standard deviation of sigma, the distribution of sample means for sample size n will approach a normal distribution with a mean of mu and a standard deviation of sigma over root n. Now that's just a very formal way of saying what we just said, in that all sampling distributions are going to have the same properties that we found with our sampling distribution. The mean is going to be the same as the population mean. The distribution will be normal. And the standard deviation is going to be a little different, but it's going to be a little different in a predictable way. So let's break this down into individual pieces and look at them one at a time. First, the shape. According to the central limit theorem, the shape of any sampling distribution, that's any distribution of sample means, is likely to be normal. It's especially likely to be normal if one of two things are true. One, the population distribution is normal. That wasn't true in our sampling distribution, if you remember. Our population had a flat distribution. But if the population distribution is normal, which it is for many things, then we're even more likely to get a normal sampling distribution. The second is that the actual size of each sample is relatively large. 30 or so is usually the rule of thumb here. Now, this also wasn't true of our sampling distribution. Our sample size was 2, and we still got a normal distribution. Now, a lot of people take that to mean that you need a sample size of 30 in order to have a good study, but that's not always the case. The sample you need for your particular study is governed by a number of factors. But if it is higher of 30, that does make it more likely that the sampling distribution you're referencing is normal. Now, the overall mean of the distribution of sample means is going to be centered around the mean of the population from which the samples were obtained. So the mean of the sampling distribution is always going to be identical to the population mean. Now, sometimes people call that the expected value of x bar. That's essentially the mean of the sampling distribution. You don't have to worry about that for now. That's just a little x with a line over it. So if you see expected value of x with a line over it, that means the mean of the standard deviation, or the mean of the sampling distribution. And as a minor note, of course, we talked about other measures of central tendency for individual scores, things like the median and the mode. But we don't talk about that when it comes to the sampling distribution. The sampling distribution, we're only ever talking about the mean. Now here's where it gets a bit tricky. Remember when we calculated our standard deviation for the sampling distribution and in the population, and they weren't the same, they didn't work out the same? Well, what I didn't mention there is that they're not the same in a really predictable way. In particular, the standard deviation of the sampling distribution is going to be the same as the standard deviation of the population divided by the square root of the sample size. Let's take a couple of minutes now and go back and work this out with our sampling distribution and see if it works out. Let's apply this formula to the standard deviations we got from our sampling distribution. So the standard deviation of our population was 2.24, and each sample was of 2. So if we work this out, Yeah. The standard deviation of any sampling distribution should work out like this. Now, the reason it works out like this is because what it's measuring is how much variability there is within the sample means, whereas the population standard deviation is measuring how much variability there is within scores. More specifically, the variability within the sample means, for that, what we're measuring is how different each sample is from the sampling distribution mean. And because the sampling distribution mean is the same as population mean, it means that what we're measuring here is actually how different the sample means are likely to be from the population mean. So remember, a sample is not expected to provide a perfectly accurate relation of its population. We talked about this in the first video. It's sort of absurd to think that any sample we draw is going to have the exact same score as our population, even though that's sort of the positivistic assumption. What the sampling distribution tells us is that we know what the chances are that it is likely to fall within this certain spectrum. It is the error of the sample mean from the population mean. It's the average distance of the sample mean from the population mean. And what that means is that we can link the sample and population through the expected difference between the sample mean and the population mean. So because the standard deviation of the sampling distribution actually gives us a pretty good estimate of how well or poorly this sample should reflect the underlying population, we actually call it the standard error. So standard error is actually really important because it is the average deviation of any sample from the sample mean. We can use any sample from the population mean. We can use it as a good marker of how good our sample is and how reflective of the population we expect our sample to be. So even if we don't know about the population, we can use the standard error of the sampling distribution to tell us how accurate our sample mean should be to the population mean. Again, this is all on average, right? Because it's the average of all possible sample means, or the average deviation of all possible sample means. So what's really interesting about this and what's great about this is that it means that in situations which we're in most of the time where we only have one sample, so we only have one sample mean and we don't know what the population looks like, if we can calculate the standard error, which we can, I'm going to show you how to do that for each of the tests we have coming up, each of the classes we have coming up, each of the different ways to calculate it depending on what kind of study you have. You can calculate the standard error, and once you have the standard error, if you can assume a normal sampling distribution, which you usually can, as we talked about, almost all sampling distributions end up being normal, and if you can infer the population mean, which you almost always can, since you know that the population mean and the sampling distribution mean are going to be exactly the same, you can figure out the probability that your sample is quite similar to the population mean based on having this standard error. So this standard error is really the linchpin that's holding this whole thing together. And a standard error, the size of it is determined by two big things. The first is your sample size. As sample size increases, the average error between the sample mean and the population mean should decrease, or the sample means and population mean should decrease based on the law of large numbers, which we're not really going to get into. Just trust that it's true. The larger your sample size, the lower your standard error. And then the second big thing is the standard deviation of the population from which the sample is drawn. So the standard error can never be higher than the standard deviation of the population. Now, you don't necessarily need to know the population standard deviation, and in most cases you won't, but you will know that it's impossible for it to be higher than the standard error. Okay, so that's a lot. I realize that this is a lot. I understand if maybe a lot of this theoretical understanding about probability is not something that you feel super comfortable with yet, and that's okay. We are just going to sort of take it slow. The big things to take away from this are, first, that any sample we draw can be generalized to a population because of the sampling distribution. That sampling distribution, the same basic one that you guys drew, although of course it's a different one for every theoretical population and every theoretical study, but they all operate the exact same way as the ones you guys drew. And it's essentially the invisible thread that tethers samples and populations together, because it allows us to predict what kind of samples we expect to get from the population, and we can estimate how likely that sample is to reflect that population. And so you'll never read a paper that talks about their sampling distribution and what they expect their sampling distribution mean to be or anything like that. But to mix my metaphors there, the engine that makes the whole thing go, it's all based on this foundation that from a broad understanding of probability and through the central limit theorem, we can make predictions about what a sampling distribution should look like even if we don't know that population information. And that means that we can take a sample and make inferences about a population through the sampling distribution because we can predict what that looks like. And every sampling distribution reflects a population in a certain way. So we can draw those lines together through this invisible thread. Okay? Now, there are big caveats here, and there's two big ones that I just want to highlight for now. Now, the first big caveat is that the sample is going to link to its actual population. By that I mean the statistical population from which you have actually drawn the sample. Most of the time, we don't know the population, right? We don't actually know the population scores. So we're inferring a population based on the sample and the predictable nature of sampling distributions. But, as you may remember from video 1, we're not usually doing random selection. The sample we choose may not actually reflect the population we think it's reflecting. So let's say, for example, I'm doing a study and I take a sample from Thunder Bay. For some reason, reading develops completely differently in Thunder Bay than it does anywhere else. So when I go to generalize my sample, it doesn't generalize properly. It doesn't apply to people from Orillia or Toronto or Ottawa because for some reason people in Thunder Bay are different, and I thought my sample was reflective of everyone, but it was actually only reflective of kids in Thunder Bay. Now that's not a problem with the sampling distribution. The sampling distribution is doing its job. It's connecting my sample, 40 kids in Thunder Bay, to the population, kids in general in Thunder Bay, but it's not connecting it to the population I had in my head because the sampling distribution can't read my mind. It's an abstract concept. Okay? It was my fault. It's my problem for not knowing what the population I was actually reflecting was. And then my second point is actually the fundamental point here. It's a connected point. We need to be really clear about what our population is in order to make the inferences from our sample. Now that's not to say we can never make inferences about a broader population than what we tested. The example I gave about testing students in Thunder Bay is sort of ridiculous. There's absolutely no reason to think that kids in Thunder Bay learn to read any differently than kids anywhere else. So a sample from Thunder Bay would probably still correspond to a sampling distribution that was reflective of a broader population, including basically all English-speaking kids in Ontario. But I do have reason to think that non-English speaking kids or kids learning English as a second language, ELL students, would learn to read differently. There's a whole other language complicating that process. So I don't think that my sample of English-speaking Thunder Bayers could apply to English language learners in Toronto or Ottawa or anywhere else, or English language learners in Thunder Bay for that matter. So there is a difference, and I know that my population the sample I have drawn is unlikely to reflect a population that includes English language learners. I know that my sampling distribution is not going to draw that line. So what that really tells us is that our understanding of our population has to be based on a theoretical understanding of our topic. I know a lot about reading and how reading develops, so I can assume how my sample is going to reflect a population, and I can infer what kind of population my sample is going to be reflecting. What factors are likely to make a difference and what factors aren't. Essentially, what factors are nuisance variables and what factors aren't going to be nuisance variables. So if you know that, then you can clearly identify your population, and then you could select a sample that could represent it, even if it's not a random sample. So then your sampling distribution can still work as long as you know that your sample is reflective of your population. And so we need to be really careful about who our samples are and who our populations are and how we think theoretically those two things are going to be related. And if we are accurate about the theoretical relationship, then the mathematical relationship will take care of itself through the sampling distribution. Okay? So for the rest of this week, what we're going to talk about is different populations and how samples may or may not reflect the population. And in fact, we'll talk more about what it means to be a representative sample and sort of try and understand how that is going to underlie the inferences and statistics and generalizations that we're going to be making.